Hey everyone, I want to give a very special welcome and a huge shout out to the Bachelor in Secondary Education math students of Romblon State University's San Fernando campus. And of course, a big hello to your professor, Dr. Villemran M. Vibas. It is so awesome to have you all here. Seriously, what you're learning right now is the bedrock of everything you're going to teach one day, and we're just so excited to be a small part of that journey with you. Okay, so let's jump right in. Today, we are going to be unpacking a concept that is, and I'm not exaggerating, one of the most fundamental ideas in all of mathematics. We're talking about the real number system. You can kind of think of it as the complete family tree for every single number you've ever used. I mean, think about it. We use numbers constantly, right? To check the time, to buy something at the store, to measure, well, anything. But have you ever just stopped and wondered how they're all connected? Where do they all come from? And how do they relate to each other? Well, that's exactly the question we're going to tackle today. We're going to build this thing from the ground up. And like any good story, our journey starts right at the beginning. We're kicking things off with the very first type of number that people ever needed. The numbers for doing the most basic thing imaginable, counting. And these are called the natural numbers. They're called natural because, well, they just feel natural. They're the first numbers we learn as kids. If you can see an object and point to it, a natural number can count it. 1 car, 2 trees, 3 houses. Super simple. So, take a look at the set. It starts with 1 and just keeps on going forever. That's why another name for them is just counting numbers. Their whole purpose in life is to answer that one simple question: how many? These numbers, they're like the bedrock, the solid foundation that we're going to build everything else on top of. Okay, but right away we hit our first little problem. Natural numbers are awesome for counting things that are physically there, but what if you look in your wallet and there's no money? How do you represent nothing? The idea of none doesn't exist in that first set. So we've got to expand our system. And the solution is actually really beautiful and simple. We just create a new, slightly bigger family of numbers called the whole numbers. The only change, we invite one new, super important number to join the group, the number 0. And let me tell you, the invention of 0 was a total game changer for humanity.
So you see how it's built? It's just all the natural numbers you already know, 1, 2, 3, and so on, but we've just added 0 to the start. Now this means that every single natural number is also a whole number. And this idea, this concept of one set fitting neatly inside another, that's a huge theme. So keep that in mind.
All right, so we can count things, and we can represent the idea of having nothing. But the real world is a bit more complicated than that, isn't it? So let's level up. It's time to solve some new problems. And to do that, we're gonna need some new numbers.
Just think about it for a second. If you borrow $10 from a friend, how do you work that down mathematically as a single number? Or what about the temperature on a really cold winter day, when it's 5 degrees below 0? Our number system right now only goes one way, up. We need the ability to go in the opposite direction too. And that brings us to our next amazing set, the integers. And the solution here is genius. For every positive number, we create a negative twin, an exact opposite. And just like that, our number line isn't just a ray anymore. It's a full line with direction. Oh, and that Z, it comes from the German word Zahlen, which just means numbers. Pretty cool, huh?
So here's our new expanded family. It stretches out to infinity in both directions, positive and negative. The latter analogy here is perfect. Think of 0 as the ground floor. The positive numbers are the rungs going up, and the new negative numbers are the rungs going down into the basement.
We're building this out really nicely. But look at our number ladder. We can stand on step 1, step 2, or negative 3, but what about all that empty space in between the rungs? How do we talk about half a cup of sugar or a third of a pizza? We need numbers for the parts of a whole.
This slide is a perfect little summary of our journey so far. Look, we started with natural numbers just to count stuff. We added 0 and got whole numbers, we added all the negatives and got the integers, and now we're at the next logical step. We've got to add fractions to fill in all those gaps.
So, let's welcome the rational numbers to the stage. And the name gives you a huge clue. They're all about ratios or fractions. The rule is dead simple. If you can write a number as a fraction, one integer over another, then it's a rational number. This includes all the integers we already know, because you can write 5 as 5 over 1. And it includes all those decimals that stop, like 0.25, and all the ones that repeat forever, like 0.666. Now, here's where the story takes a really cool twist. For a very long time in human history, people thought, that's it, we're done. The rational numbers have filled in all the gaps. It seemed like they covered every possible point on the number line. But they were wrong. There was a secret, totally different kind of number hiding in plain sight.
This slide lays out the big difference. Think of it like this. A number is either one or the other. It can't be both. Rational numbers are, well, they're tidy. Their decimals are predictable, they either stop or they repeat in a nice pattern. Irrational numbers, they're wild. Their decimals go on to infinity and beyond with no repeating pattern whatsoever.
And you've already met the most famous members of this family. You've got pi, the star of every circle. You've got the square root of 2, the number that actually proved these guys exist. And you've got e, which is just so important in things like finance and calculus. These aren't just weirdo numbers, they are absolutely essential for describing the world we live in.
Okay, so we have our two big groups of numbers. We have the nice, orderly rationals, and we have the wild, unending irrationals. So what happens when we finally bring them all together? We finally get to see the complete picture, the real deal.
And there it is, the whole shebang. The real number system is made up of two distinct teams that never mix, Team Rational and Team Irrational. And look over on the rational side, you can still see our nested sets. Naturals live inside of wholes, which live inside of integers, which live inside of rationals. And when you take those two big teams together, you get the entire real number line.
Now, for all of you at Romblon State University who are going to be math educators, this is so much more than just a chart. This is the blueprint. This is the schematic for your entire mathematical toolkit. Every single thing you teach later, algebra, geometry, calculus, it all stands on this foundation. Really, truly understanding the structure is what separates a good teacher from a great one.
So, we've come to the end of our explainer on the real number system. But really, your own journey of discovery is just getting fired up. So what's the next step for you?
Well, to make sure that you keep getting lessons and explainers just like this one, I really want to invite you to head over to the No Problem Only Solution YouTube channel. Go on, hit that subscribe button, give this video a like if it was helpful, and please leave a comment. We really do love to hear from you. And I'm going to leave you with one last question to mull over. We've built this huge, beautiful system that seems to cover every single point on the number line. But is that everything? Could there be other numbers out there? Numbers that don't even live on this line at all? Numbers that exist beyond it? Keep on asking those big questions, keep exploring, and we'll see you in the next explainer.